Hello everyone. Ray optics and optical instruments part 4. Refraction and dispersion through a prism. First we can see refraction through a prism. So this is a prism ABC. Now we can consider an incident ray PQ. When it meets the face AB, it undergoes refraction. Here I is the angle of incidence and R1 is the angle of refraction. Now when this ray reaches the other face AC, this undergoes refraction. But since the ray of light passes from a denser medium to a rarer medium, that is from glass to air, the refraction is such that it bends away from the normal. Here, E is the angle of emergence and R2 is the angle of incidence after refraction at Q. Now, considering the quadrilateral AQNR, we can see that angle A plus angle QNR is equal to 180 degree. And from triangle QNR, we get R1 plus R2 plus angle QNR is equal to 180 degree. From both these equations, we get R1 plus R2 is equal to angle A, the angle of the prism. Therefore, the total deviation delta is equal to the sum of the deviations at both the interfaces, that is I minus R1 plus E minus R2. That is delta is equal to I plus E minus angle A. Based on this equation, it is possible to draw a graph between angle of deviation and angle of incidence. From the graph, we found that the angle of incidence and angle of emergence are symmetric to each other and hence can be reversed to get the same result. Now, we can consider a special case, that is the angle of minimum deviation. This is the case when the refracted ray at Q is parallel to the base BC. In this case, the angle of incidence and the angle of emergence becomes equal and hence R1 is equal to R2. Therefore, angle A, which is given by R1 plus R2 is equal to 2R, or R is equal to angle A by 2. So, delta, which is equal to dm in this case, is equal to 2I minus angle A, or I, which is the angle of incidence, is equal to dm plus angle A by 2. Now we can find the refractive index of the material of the prism, N21, which is equal to, by Snell's law, sin I by sin R. That is, sin of dm plus angle A the whole by 2 divided by sin of angle A by 2. In the case of a small angle prism, N21 can be written as almost equal to dm plus angle A by 2 by angle A by 2, or dm is equal to N21 minus 1 into angle A. Now we can consider the dispersion taking place in the case of a prism. That is, dispersion is the phenomenon of splitting of light into its component colors. The pattern of color components of light is called the spectrum of light. The spectrum of light is as shown in this figure. That is, white light is incident at one face of a prism, and the final emergent ray consists of the constituent colors of the white light, which is the white light spectrum. Now, the cause of dispersion is because the refractive index of medium for different wavelengths is different. So, the variation of refractive index with wavelength depends on the media. In the case of a prism, it is glass. But in vacuum, the speed of light is independent of wavelength. Thus, vacuum or air approximately is a non-dispersive medium in which all colors travels with the same speed. We can consider thick lenses as made of many prisms. Therefore, thick lenses show chromatic aberration due to the dispersion of light. Now we can see some natural phenomenon due to sunlight. First is the rainbow. Rainbow is formed as a result of refraction, reflection and dispersion of sunlight. The rainbow is an example of dispersion of sunlight by the water drops in the atmosphere. This is a phenomenon due to the combined effect of dispersion, refraction and reflection of sunlight by the spherical water droplets of rain. Sunlight is first refracted as it enters a raindrop, which causes the different wavelengths, that is the colors of white light, to separate. Longer wavelength of light, which is red, are bent the least, while the shorter wavelength, which is the violet, are bent the most. Next, these component rays strike the inner surface of the water drop and get internally reflected. If the angle between the refracted ray and normal to the drop surface is greater than the critical angle, it is 48 degree in the case of a water droplet. The reflected light is again refracted as it comes out of the drop. It is found that the violet light emerges at an angle of 40 degree related to the incoming sunlight, and red light emerges at an angle of 42 degree. For other colors, angles lie in between these two values. These are shown in this figure. Now, in the case of the formation of a primary rainbow, the figure is as shown. That is, the violet from drop 1 and red light from drop 2 are directed at level above or below the observer. Thus, the observer sees a rainbow with red color on the top and violet on the bottom. Thus, the primary rainbow is a result of three-step process, that is refraction, reflection and refraction. Now, in the case of a secondary rainbow, it undergoes two total internal reflection. That is, instead of one, as in the primary rainbow. A secondary rainbow is having lower intensity of light, and hence the secondary rainbow is fainter than the primary rainbow. Now we shall see the phenomenon of scattering of light by the Earth's atmosphere. Scattering or change in direction of sunlight happens by particles in the Earth's atmosphere. Light of shorter wavelengths is scattered much more than light of longer wavelengths. It was Rayleigh who gave that Rayleigh scattering criterion, which gives that the amount of scattering is inversely proportional to the fourth power of the wavelength of light. Now we can explain why the sky appears blue. The bluish color having a shorter wavelength than red predominates in a clear sky due to stronger scattering. Violet also gets scattered even more than blue due to its shorter wavelength. But since our eyes are more sensitive to blue than violet, we see the sky blue. Now we can see for particles having size A, such that the particle size is very much lesser than the wavelength of light, Rayleigh scattering occurs. And for A very much greater than lambda, which is the wavelength of light, there is large scattering objects like ice pieces, large dust particles, or large water droplets. All wavelengths are scattered equally. Thus, clouds having large water droplets are white. Now, another fact due to scattering is at sunset or sunrise, the sun's rays have to pass through a larger distance in the atmosphere. Most of the blue and other shorter wavelengths are removed by scattering. The least scattered light reaching our eyes, therefore, the sun looks reddish. This explains the reddish appearance of the sun and full moon near the horizon. So this is the end of this video. In this video, I have explained refraction and dispersion through a prism, the theory behind rainbow, and scattering of light. If you have got any doubt, please comment in the section below. Thank you.